Hey everybody, Dr. A here, and in this video we're going to be providing some background information on another cross-section property of members. This particular property we're going to talk about is called moment of inertia. It's also sometimes called the second area moment, and we're going to be following along in the Hibbler Statics textbook published by Pearson. So if you have a copy of that book, it'd be great to follow along with that as you go through this video. But before we get started with this material, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's dive into it now.
In this video, we're going to be discussing a new topic, which is called moment of inertia, as well as we're going to be getting into what's called the parallel axis theorem. So these are going to be the first couple of sections in chapter 10. So what is moment of inertia? So this word moment of inertia is sometimes called second moment of area about an axis. Okay, now a moment of inertia for our purposes is going to be a cross-section property of a shape, or it's a geometric property of a particular two-dimensional shape. Now, there's also something called a mass moment of inertia, which you would learn more about maybe in a dynamics course. But for our purposes in a statics course, we're learning about moment of inertia as it pertains to an area, geometric property involving area. Okay, so moment of inertia, we typically use moment of inertia. We typically use the capital letter I for moment of inertia. Okay, so capital I. Now, you always are computing the moment of inertia about an axis. Okay, so when we say I sub x, we call this the moment of inertia. Spelled that wrong. About the quote x axis. And then of course we have something called I sub y, which is moment of inertia about the y axis. And then we have something called j, which is sometimes called the polar moment of inertia, which is the moment of inertia about the z-axis. Okay, now all of these values have units of length to the fourth power. So we're going to say I sub x, I sub y, and j, all have units of length to the fourth power. Okay, and by the way, polar moment of inertia, which has the letter J, I'll put a note here. This is also sometimes labeled as I sub z, but more often it's labeled as J. Okay, so now let's talk about these units for a second. We have units of length to the fourth power. That seems a little confusing. That really does not have much of a physical meaning. It just happens to be length to the fourth power, so please don't try to rack your brain on what that actually means. Okay, so let's try to draw a little figure and see kind of what we're talking about. So I'm going to go ahead and I'm going to draw a set of XY axes. Okay, and I'm going to say I have some kind of area here, all right? And let's call this my area A, all right? And what we're doing is we're going to look at this little differential area, all right? And we're going to say that this differential area has a perpendicular distance from the x-axis called y, and we're going to say that it has a perpendicular distance to the y-axis called x, and then we're going to say it has a radial distance to the origin called r, okay? And so the way we compute this moment of inertia of this area about an axis is the following. We're going to say I sub x equals the integral over the area of y squared dA, okay? So one way you can kind of think about this is if you're taking a moment of this area about this axis right here, okay? And your perpendicular distance is y, okay? From a differential area to the x-axis. In fact, let's go ahead and label this little area as dA. All right, but in the formulation you're squaring it. Okay, that's why we sometimes call it the second area moment of inertia. All right, and then likewise you're going to have the moment of inertia about the y-axis is integral over the whole area A x squared dA. And that x value I'm talking about right here that I am squaring is represented by this perpendicular distance. And again, the y squared I'm talking about in the I sub x formulation is this y value here. And then similarly, our polar moment of inertia, which we sometimes call IZ, but I'm calling it J, is equal to the integral over the area of the radius, this radial distance squared, dA. Okay, now if you notice, this little radial distance forms kind of a hypotenuse with a y component and an x component. So another way you can express J is just I sub x plus I sub y, okay? So that's how we can kind of express that, and if you can kind of see this Pythagorean identity is built into these moment of inertia calculations, all right? So that's kind of the background of it. Now, the thing to keep in mind is y and x, these are represented by perpendicular distances here. So for function values, they're not necessarily going to be the value of a function necessarily. So we're going to say, just make a note here, x and y are perpendicular distances, okay, from a differential area dA to the axis that we're trying to take a moment about, the moment of inertia about. All right, so in terms of nomenclature, you always have to say moment of inertia about a particular axis. You can't just say what's the moment of inertia. You have to say what's the moment of inertia about the x-axis, what's the moment of inertia about the y-axis. Now, when we're considering these integral forms, the important piece of this integral to really take a look at is dA, okay? Notice we have these dA values because we're integrating over this area. So how do we take into account this dA? So in general, dA can be written as either dA equals y dx or dA equals x dy. And how do you know which one to write it as? Well, it doesn't really matter, but one way will be smoother going for you than another way. So in general, we're going to say this. We're going to say it is best to orient dA parallel to the axis we want to compute I about. So when we do some practice problems here in a few minutes, let's take a look at a couple of illustrations, okay? And this will help us set up how we're going to do practice problems. Let's say that we have some kind of area like this, okay? And let's say we want I sub x, okay? If we want to compute I sub x, to compute I sub x, then follow this sentence right here. It is best to orient dA parallel to the axis we want to compute I about. So for I sub x, I would say we should orient dA like this. And so when you orient dA, what is this dimension right here? This vertical dimension is dy, okay? And then the width dimension right here is what? Is our x value, okay? So to compute I sub x, we're going to say use dA equals x times dy, okay? And again, our little differential slice becomes parallel to the axis that we want to compute the moment of inertia about. So what about if we wanted dy for the same area, not dy, I'm sorry, iy. What if we have the same area and we want iy, okay? So I'm going to say to compute iy, use dA equals what? Y dx. Again, you make your slice parallel to the axis that you're trying to compute the moment of inertia about. So the width here is dx, and then the height is a distance y, okay? Now, again, this isn't the only way to do it, but this is the most convenient way that can minimize confusion and headache with computations, all right? So when we get to some examples later on, we're going to take this approach. If we want Ix, we're going to say dA is x dy, and if we want Iy, we're going to say dA is y dx, and you can visualize it like this. The next thing we're going to talk about in this video is what's called the parallel axis theorem. So what this allows us to do is the following. We can apply what's called the parallel axis theorem to compute the moment of inertia about any axis that is parallel to the centroidal axis. So let's write that down. We're going to say compute I about any axis parallel to the centroidal axis in a given direction. Okay, so for example, let's say that we have the following. Let's say that we have our xy coordinate axes here, and let's say that here is our area, and let's say that we know the centroidal axes. Let's call them maybe x prime and y prime, okay? So I'm going to say let x prime dash y prime be the centroidal axes of the area. So if I know that, if I already know my x prime and y prime axes right here, the location of the centroid, then and I know that moment of inertia about those centroidal axes, then I can compute the moment of inertia about any other set of axes, given the fact that I know it already about the centroidal axes. So the way we would write that mathematically is, let's say that I want I sub x. I would say I sub x is equal to I sub x prime plus a times d sub y squared. And d sub y is going to be this distance right here. Okay, so I'm going to say d sub y is the perpendicular distance between the x prime and x axes. Okay, and again, when I say x axis right here, this right here, that's any axis, that's any horizontal axis, which of course is parallel to my centroidal x prime axis. And in a similar way, I can say the following. I can say the moment of inertia about any vertical axis, any y-axis. I mean, that could even be over here somewhere, okay? Any vertical y-axis is equal to the moment of inertia about the centroidal y-axis, which I call my centroidal y prime axis, plus a times d sub x squared. And d sub x is this dimension right here, d sub x, okay? So we can also, in a similar way, use the parallel axis theorem for the polar moment of inertia as well. So you can read more about that in the textbook. So that's what the parallel axis theorem allows us to do. Now, why is all of this important? Okay, just to kind of wrap it up in this background video, I'll put a star here. All of these properties are used to compute strength and deflection properties of materials. So when you get to later classes like mechanics of materials or structural analysis or machine design or dynamics, all of these later classes in engineering will be based on this information that you're learning in this statics course. So this may seem a little abstract right now, but it is tangibly applicable to concepts in your later engineering courses.